Hey everyone, I'm Shah. In this video, I'll discuss how to fine-tune a large language model to use tools. I'll start with a high-level overview of what we're trying to do here, and then walk through a concrete example with Python code. So just to level set here, let's answer the question, what is fine-tuning? And all this is adapting a model to a specific use case through additional training. The analogy I like to use here is to think of the base model as this raw stone that we've just extracted from the earth, and while it has a lot of potential, it in of itself isn't super useful. But what we can do with the base model is chisel and refine it into something that's a bit more aligned with our use case. So this is exactly what happens when the various AI labs train base models such as GPT-3 or Llama 3.2 base, and then refine these base models to follow instructions in a process called instruction tuning. But we can go one step further. We can take these instruction tuned models, which are already more helpful than the base model, and we can make them even more helpful by fine-tuning them to do yet another behavior. Instead of just following instructions, we'll also fine-tune a model to use tools. So that's exactly what I'm going to walk through in this video. But how do we do this? The way we fine-tune models is the same way we train models. We give them examples to learn from. And so these examples are called our training data. In other words, these are illustrative examples of the behavior we want the model to learn. For example, if we have an instruction tuned model and we ask it something like, what's 1000 times 923.01 divided by 3 to the power of 4? Modern instruction tuned models, they'll probably do something like this, where they'll break down the calculation into steps. So they'll first do 3 to the power 4, then do the multiplication, and then divide everything. And while this will give better results than if the model just tries to answer this math equation in one shot, this is still not the right answer. This is one of the fundamental limitations of large language models. They're not really good at doing math or very precise calculations or tasks. And so this is not what we want our large language model to do. Instead, when it gets a question like this, where we know it's not one of its strengths, we can have it call a tool. What this means is, instead of having the model actually respond to this query, we're going to have it respond with a output with a special structure, and then we can parse this structure and actually call this tool. In this case, we see the large language model is calling a calculator tool, and it's passing in a query to this calculator tool, which is exactly what the user typed in. What we can do with this from a practical standpoint is, anytime we see the large language model generate a structured output like this, we can parse it, see what tool it wants to call, and then we can write some Python code to execute that tool, generate an output, and then we can feed that output back to the language model so it can generate a helpful and accurate response to the user. And so this is the behavior that we want the model to do. So to pull this off, we're going to need to construct a bunch of examples of conversations like this so the model can learn this behavior. We'll need at least hundreds of examples, but more examples, given that they're high quality, is going to be better. Here's just an example of what this might look like. A trace is simply a full conversation between a user and assistant, and might include other types of roles. So here's an example of the examples that we're trying to generate in a Llama style chat template. So I know there's a lot going on here, but I'm going to break down step by step. First thing is that we have these special tokens, which I've colored in green, and then we have various roles for each of these messages, and then we have the actual messages in white. We see Llama has these special tokens of begin of text, start header ID, end header ID. These are just identifying who is talking. So this is a system message, which is you are a helpful assistant, and then there's an end token, then another start header. Now the user is talking, and we have that same question. What's 1000 times 923.1 divided by 3 to the power 4? Then we have another end token, and now it's the assistant's turn to talk. But instead of responding, the assistant is generating a function call. And so in the case of Llama, this is what function calls look like. It'll start with a Python tag and then function calls will kind of look like Python code. So be like a module dot whatever method you're trying to call. So let's say we have a Wolfram Alpha tool available. We can do Wolfram Alpha dot call, and then we can pass in our query. We'll have an end token. And now we have a special role called IPython, which is where we can put the results of this function call. So we can have the function call be in this very structured JSON format. We'll have another end header. And now the assistant has this full context when it starts to generate an answer. And then it can come up with the right answer because it actually used a calculator to do this. An important note here is that this initial assistant message and this IPython message is not something we need to show to the user. From the user's perspective, they just asked this question and then they got this response. These are the kinds of traces that we want to generate in order to fine-tune a model. So we want hundreds or even thousands of these traces. To make this all more concrete, let's walk through a specific example. Here I'm going to fine-tune Gemma 3 1B to use tools. Gemma 3 is an open weight model from Google. The version I'm using here has 1 billion parameters, which means it can run pretty easily on my MacBook. For all the training and everything, I'm going to be using the Hugging Face ecosystem, and all of this is going to be coded in Python. And so here's a quick overview of the key steps. The first thing we want to do is define the tools that we're going to use in our training data. And then from there, we can generate queries that require calling these tools that we've defined. And now that we have queries, we can generate these full traces. So including things like system messages, user queries, assistant responses, assistant function calls, the results of these function calls. And we'll have like different varieties of these conversations. And then once we have that, we can fine tune our model on these traces. And then finally, we'll evaluate the model to see if it's actually improving on this ability to call tools. And I'll just call out that all the code for this project is freely available at this GitHub repo, which I've linked in the description. Also, the data set that I used and the fine-tuned model are freely available on the Hugging Face Hub, also linked in the description. The first thing we want to do is define tools. So my thinking here is I wanted to define as many tools as possible because I didn't want to just define like 1 or 2 tools and risk the model only learns how to use those 1 or 2 tools and not generalizing to other types of tools. The way I approach this is I first brainstormed with ChatGPT and Claude separately, and I even went kind of back and forth. So I'd get a list from ChatGPT, and then I would pass that list to Claude, and then I'd pass it back to ChatGPT. Eventually, I came up with 40 different tool ideas, and these are things like a calculator, querying a SQL database, creating a calendar event, sending a Slack message, searching the web, doing date time calculations, doing currency conversions. So a lot of things that large language models may struggle with. Once I had these tool ideas, I had Claude via cursor generate me this tools.yaml file where each tool had this structured metadata where we had its name, a description of it, and then all its input parameters. So we had these parameters, these properties, and then this tool, the calculator tool, took in a expression input, which was a string, and we had a description for each of the input arguments. So we have this tool metadata, and then from here, I just had Claude take the next step and implement all these tools in Python. And so the important thing here is that a lot of these tools will like require, querying a SQL database or searching the web or getting the weather in a city. So in order to make these queries verifiable and easy to run, I created a bunch of synthetic data to actually make these function calls. So basically here, I'm just like simulating the function call. I'm not actually grabbing the weather in San Francisco or something like that. I just have these things like pre-baked into this tools.python file. And if you want to check out the tools.yaml file or the tools.py file, they're both freely available at the GitHub repo, so you can read through all the function definitions. Now that we have the tools, we can generate synthetic queries for them. For all the queries, I used GPT 4.1, and I actually created 3 different types of queries. I created queries that didn't require tool calls. And so this is really important because if I only fine-tune the model on examples that require tool calls, there's going to be a risk that the model will just call tools for everything and we'll just forget how to answer questions and just have regular conversations. So I generated synthetic no tool examples. I generated synthetic easy tool examples. So basically this is where a tool call is needed, but it should be something pretty straightforward. straightforward. So the model can directly from the user's query generate a tool call. It doesn't need to do any kind of reasoning before that. And then I had hard tool calls, which also require tools, but might require some thinking before being able to know which tool to select. So at the end of this process, I had 600 total queries where I had 200 of each of these subtypes. And then if you're curious about the code I used to generate it, if you go to the GitHub repo, it's this file 1-genqueries.ipy notebook. And so there you'll see the prompts and the code I used to get GPT 4.1 to make all these queries for me. Now that we have the queries, we can actually generate these traces for them. And so since we had 3 different types of queries, the traces for these 3 types look slightly different. So for the no tool queries, the traces looked something like this. I had an initial user message, which consisted of the high-level system instructions, like a system message, and the tool metadata. The reason I didn't use a system role here is because Gemma only was trained on 2 roles. There's a user role and a model role. So unlike Llama, which had those 4 different roles of system, user, assistant, and IPython, Gemma only has 2. So I had to work within those constraints to make these traces. After these high-level instructions, I inserted a query from this no tool query list, one of the 200 different no tool queries I have. And then I just generated a response. Because no tool call is required, I just had Gemma 3n e4b instruction tuned generate a response. I did this using together.ai. And the reason I didn't use Gemma 3.1b is because I couldn't find that hosted anywhere, and I wanted to generate these pretty quickly, and running inference of Gemma 3.1b on my laptop would be a lot slower. Then for the easy queries, the initial messages were exactly the same. So I had these instructions and tool metadata. Then I inserted the easy query, but instead of generating a response, I had GPT 4.1 generate a tool call. So this was in a structured JSON format, which we'll see on the next slide. And then I actually called the tool using the implementations that we talked about on the previous slide. Then I extracted the tool result and passed that as a user message. So the tool result was inserted into the context. And then finally, I had Gemma 3n e4b it generate a response just like before. And then for the hard queries, the process was very similar, but instead of just having GPT 4.1 do a tool call, I highly encouraged it to write out its thought process first and then generate a tool call. I did this because I wanted to teach the model this behavior of not just doing tool calls directly from particular queries, but learning how to reserve some space before the tool calls to kind of think through the problem of understanding the user's intent of the tools provided in the tool metadata, because this won't include just one tool, it might include 1 to 40 different tools, selecting the appropriate tools and then figuring out how to use that tool. So reserving some tokens for the model to reason about that. But this didn't really work as expected. I actually had to drop these hard examples from the training data, and I did that because it just wasn't working with the hard examples, like the model wasn't improving. And I think it's for a couple of potential reasons. One, the thinking tokens were generated by GPT 4.1, so maybe the way Gemma thinks and the way GPT thinks is fundamentally different, so maybe that was throwing it off. And then the second reason might be because the hard queries weren't actually that hard. There may have been some cases where the hard query was really an easy query that the model didn't need to generate any thinking tokens before doing a tool call. And then of course all this code is in the GitHub, and this is the file name to check out. Let's look at a specific chat template. And so the special tokens for Gemma are pretty similar to Llama. So there's a begin of text token, there's start header ID. So the first message is the user message, but then within the first user message, I added some structure. So I added these instruction tags and tools tags. I didn't define these as special tokens. These are just going going to be strings to the model, but it does add some structure to the initial message. Put the system instructions here within the instructions tags, and then I put in a list of the tools with metadata within these tools tag. And so I actually varied this, so some traces had just one tool in them, and maybe that was the correct tool to use. Other traces had all 40 tools and everything in between. The reason this is important is because in practical situations, you might have dozens of tools that the model can choose from, and you may not know what tool is going to be needed by the user at the outset. So the model needs to decide that at inference time. And then we have another user message. So I inserted the query here, and then this actually continues. Then was the assistant message. If no tool call was required, the assistant would just respond. But if a tool call was required, I added these special tool call XML tags. And so the tool call was actually some JSON text that included the tool name and the input arguments. And so it's important that we have the tool calls within special tags, because this is going to make it a lot easier to parse at inference time. So basically, anytime we see this end tool call tag, we know to stop inference, execute the tool call, get the result, and then the result I would inject into this next user message, and then this should be tool result, not tool call. So I added these tool result tags in this next user message. And then finally, the final assistant message has this full context of the tool call and the tool result, and then it can generate its final answer. And then I also encourage the model to put its final answer in these final answer tags, because maybe it's generating a lot of tokens to reason about these things, and we only want to display the final answer to the user. If you want to see an example of this, check out the dataset on the Hugging Face Hub, and you can read through the hundreds of different traces that I used here. Okay, so there's actually a bonus step between steps 3 and 4, which is to actually refine the traces and do a little bit of data prep. There were 5 things I did here. The first thing is I added answer tags to some of the traces. The no tool call traces didn't have the answer tags in them, so I manually added those. But then there were also a bunch of bad tool call traces. Basically, when I would look for an answer tag in some of the tool call traces, they were missing, so I had to manually add them. Here's an example of a bad tool call. So basically, the model uses the right syntax, but the tool call may have failed because it didn't pass in a proper input. Compute median is a tool, but it's supposed to pass an array of numbers, not include its description. For these, I would have to manually fix them, or if it wasn't clear how to fix them, or fixing them would have taken a lot of effort, I just dropped them. So I ended up dropping 3 traces from the data set. And then from there, I created a train test validation split. So I saved 80% of the data for training, 10% for testing, and 10% for validation. Finally, I pushed the dataset to the Hugging Face Hub. The code for this intermediate step is in the 3-dataprep.ipy notebook. Now that we have all the data ready to go, we can fine-tune the model. Here we can just, with one line, load in our dataset. But like I mentioned earlier, I had to do some filtering of the training data because it just wasn't working. When I would fine-tune on all of the data, the model was actually getting worse. The instruction-tuned model was outperforming the fine-tuned model. So after many iterations, I finally landed on this training dataset where I kept all the easy query traces, and then I kept 20% of the no tool call traces, and then excluded all the hard tool call traces. So I have this filter dataset function, and then I can apply this filter to the entire dataset. Next, we can load in the model and the tokenizer. So I loaded in Gemma 3 1B instruction tuned from the Hugging Face Hub. Use this auto model for causal LM from pre-trained. So just pass in the model name, the device. I'm on Mac, so I used MPS. And then attention implementation eager. So this is what Google recommended on the Gemma 3 1B model card. So that's why I did that here. And then the tokenizer is a one-line import. So we just do auto tokenizer from pre-trained, and then we pass in the model name. Now that we have our tokenizer, we can tokenize our training data. And so I created this preprocess function, which will preprocess the data one row at a time. One note here is that Hugging Face has this apply chat template function, which will automatically add the special tokens and put the chat in the proper format, because the training data set I have has the traces as a list of dictionaries where each message is a dictionary with a role and the content, and then messages are grouped together in a list. The apply chat template function requires alternating roles. So it requires like system, user assistant, so on and so forth. But the problem is that first user message I basically used as a system message, but the apply chat template function doesn't work like that. So for each row, I had to replace the role of the first message with system. And so this is how we do that. Each row has this trace feature. So this will be a list of messages, and then we can grab the first message, and then we can reset the role of that first message. And then we can tokenize the text. So we apply the chat template to all the messages in this list, or actually we're not going to be tokenizing it. We're just going to be applying the chat template because it gets tokenized on the fly during training. So the main thing we're doing here is resetting the initial role to system, and then we're applying the chat template. So adding in all the special tokens to these traces. And then it's pretty easy to apply this to the entire data set with this map method. The next thing we're going to do is set up LoRa, which is short for low rank adaptation. It is a parameter efficient fine tuning approach. So 1 billion parameters, while that might be small in the context of modern large language models, it's still a lot to run on a laptop. LoRa allows you to fine tune models by only training a relatively small number of parameters. Here are the hyperparameters I used here for LoRa. So rank basically is controlling how many parameters we're going to train. Alpha is kind of like a learning rate for LoRa. Dropout helps prevent overfitting. So randomly 5% of the weights will be set to 0 during training. And then modules, I did all linear. And so there were a couple of resources that were helpful in figuring out what are good hyperparameters for this. References 5 and 6. One is a example of fine-tuning Gemma for OCR from Google. And then there's another post on Medium, which does a similar thing. They fine-tune maybe Gemma or Llama to do function calling. That's always a good tip. If you're trying to fine-tune a specific model on a specific task, go try to find what has worked for other people and then use that as a starting point, because there's a lot of hyperparameters to pick. Now that we've set up LoRa, we can also set up the hyperparameters for training. Learning rate, I did 2 to the minus 4, trained for 3 epochs, batch size 1, and that was just because of memory issues on my MacBook. And then I defined a fine-tuned model name. Here are all the training arguments. We can have an output directory where we save the LoRa weights, number of epochs, learning rate, batch size per device, gradient accumulation. Gradient accumulation is basically the number of steps it takes to actually update the parameters. So this is helpful if you have a small batch size. You can increase the gradient accumulation steps and it'll basically be like having a larger batch size. Warm-up ratio, basically there's going to be a linear increase of the learning rate for the first 3% of examples. Max gradient norm, so this helps prevent crazy updates, so it keeps the update steps relatively small. Eval strategy, the save strategy, so this is just saying that we're going to evaluate the model every 20 steps. We're also going to save it every 20 steps. We'll load the best model at the end, and best in this case will be the evaluation loss instead of the training loss. And then we can train the model, so we just pass everything into a SFT trainer. This is from the TRL library from Hugging Face. We have our training data set and then validation data set for evaluation, and we pass in our PEFT config to do the LoRa training. And then we just train it. Here are the results. Both the training loss and validation loss are going down, which is a good sign. And you can see the full Python notebook here. It's for fine-tune model.ipy notebook. So things are looking good so far, but just because the loss is going down doesn't necessarily mean that the model is getting better at function calling or it's something that's going to be helpful to us. Basically, every training run I did, the loss looked good, but then when I would go to the evaluation step, there were some problems. So it's important that we evaluate the model to make sure it actually does what we want it to do. So I looked at these 3 evaluation metrics. The model called a tool when a tool call was needed. So that means it called a tool on an easy or hard query, and it didn't call a tool on a no tool query. So surprisingly, Gemma 3.1BIT did a pretty good job. It had a good understanding of when to call a tool and when not to call a tool, but we did get a little bit of lift when fine tuning. But this is where we see the biggest difference. Gemma would call tools, but a lot of times it wouldn't call the right tool. So it only did it 35% of the time compared to the fine-tuned model, which did it most times, 52% of the time it called the right tool, then successful tool calls. So even though Gemma called the wrong tool many times. The tool calls were still successful half the time, but we did get some lift, so like 17% lift when fine-tuning. So let's see an example of how the instruction tuned model may have gotten it wrong. Here we have what I think is a hard query, or maybe not a hard query. Hey, what day of the week was 2023 12/13? This isn't something that a model will probably be able to do without using a tool. The original model did correctly realize that it needs to use a tool. Looking at the structure, did a good job. It looks like the fine-tuned model, but if we look a little closer, we see that the tool name is completely wrong. Computing the median is not going to help with this. Also, the input to the tool call is completely wrong. It just says the description rather than actually providing a list of numbers. On the other hand, the fine-tuned model used the correct tool, so get weekday from date, and then it had the correct input, which is 2023 12/13. All the code to do the evaluation is in this 5 eval model IPy notebook. Okay, so that's basically it. This was one of the most time-consuming projects. Creating the synthetic data took about a week, and then getting the fine-tuning to work actually took longer than expected. So that took like a day and a half. But hopefully this video helps you do that in much less time. All the code's on GitHub. You can even steal the training data on the Hugging Face Hub. And then if you want to try out the model, it's also freely available on the Hugging Face Hub. And the links for all this stuff is in the description. So if you have any questions or suggestions for future content, please let me know in the comments below. And as always, thank you so much for your time, and thanks for watching.